When you think about the North Pole, you don't expect it to go anywhere. And you certainly don't expect it to change places with the South Pole. That would just be wrong. Our magnetic compasses would all point the wrong way. We'd need to update our maps. Birds would probably be horribly confused. And yet, although they sound like something out of science fiction, geomagnetic reversals like this are real. They've happened before, and the process behind it might be a lot more dangerous than you'd think. To be clear, it's not the reversals themselves that are potentially dangerous, it's the buildup. During those times, the Earth's magnetic field, the shield around our planet that keeps us safe from deadly solar radiation, will drop to as low as 10% of its current strength, leading one group of scientists in 2021 to predict climate shifts and mass extinctions, and others to describe satellites being destroyed, electrical grids going offline, and deadly radiation raining down on us for hundreds or even thousands of years. This is troubling when you consider that we are a couple of 100,000 years overdue for our next geomagnetic reversal, and based on fluctuations in the Earth's magnetic field that scientists are detecting right now, the build-up to a geomagnetic reversal may even have begun already. Which begs the question, should we be worried? I'm Alex McColgan and you're listening to the Astrum podcast. Join with me today as we explore the science behind geomagnetic reversals and find out whether the next one will be an apocalyptic scenario or whether it'll lead to nothing more than a few lost birds. What truly happens when things go south? Let's start by trying to understand where the Earth's magnetic field comes from in the first place. It's not a given that our planet would have a magnetic field. The two planets flanking us, Mars and Venus, do not have one, and yet the Earth does, which is a good thing, as without one, there is a very real chance life would not have been able to arise here in the first place. Thanks to the protective cocoon of this field, deadly solar radiation is deflected away from the planet's surface, allowing things to flourish without all that radiation breaking down our DNA, causing mutations and cancers. Scientists are still trying to figure out all the particulars of why certain planets have fields and certain others don't, but the current leading theory is that the Earth's core acts as a giant dynamo. It's a principle of physics that you can use electrical fields to create magnetic ones, and vice versa. This is the principle that power plants work under. Moving a magnet through a coil of wires causes electrical current to start to flow, as that changing magnetic field exerts a force on the electrons present there. But similarly, the motion of electrons creates a magnetic field to form in perpendicular circles around the direction of motion, in accordance with Faraday's law of induction. But the way this applies to the Earth's core is a delicate, complicated process. To start with, our core needs to be at least partially liquid, which fortunately is true. Above the solid inner core that lies at the heart of our planet is a liquid outer core, where the pressure isn't quite high enough to keep things in a solid state. It's very hot in the outer core though, 6,000 degrees Celsius at its warmest point, so hot that it rivals the surface temperature of the sun, which, when combined with the lower pressure compared to the inner core, is more than enough to keep the iron and nickel that makes it up flowing down there. The temperature drops as you move away from the center of the Earth. This gets circulation going. Hot, conductive material from the warmer, deeper regions of the outer core rises, then cools, then falls again, creating loops and currents of flowing material. Our electrical field starts to be generated. But if there are many of these flowing loops, which in theory there would be, why does Earth only have one North Pole and one South Pole? Surely the created magnetic fields would be all over the place. Well, there is thought to be an extra force at play that takes all these fields and unifies them, pointing them in the same direction. This force is thought to be the Coriolis effect. Dynamo theory states that the Coriolis effect causes these flows of iron to not rise and fall as straight lines, but as spirals. The spinning of the Earth causes them to gently be spun in turn, creating giant springs. As each segment of each spring is creating a magnetic field in a circle around it, the net result is that the inside of these springs creates a solid, unified field that all moves in the same direction upwards, while the outside brings that magnetic field looping back down again and back in to the bottom of the coil. In short, it creates the well-known magnetic dipole north and south that we see today. However, if there's anything that you should take away from this, it's that this process is precarious, as it is based on a lot of liquid iron essentially just sloshing around, which is not very consistent. Our magnetic field thus has little fluctuations and wobbles all the time. We see this in different ways, but a big one is that our North Pole is constantly moving. Since scientists began keeping track of it in 1831, the North Pole has gradually shifted about 1,100 kilometers, leaving its original location in Canada and moving up towards Siberia. Its rate of motion is also increasing, going from 16 kilometers a year to roughly 55 kilometers a year, a big jump. This might still be akin to just the momentary wobbles of a spinning top though. Yes, it deviates somewhat, but it always remains roughly upright. That's a far cry from a complete reversal. However, scientists are certain that such reversals have happened before. They even have a specific number, 183 times in the last 83 million years. How do they know? The answer lies locked in our Earth's surface iron. When magma erupts from the Earth's mantle, it can contain small amounts of iron. As these can move freely in the molten magma, they tend to orient themselves in the direction of the Earth's magnetic field. However, scientists noticed that there were layers of geological history where the iron was pointing one way and layers where it was pointing in the reverse direction. Their explanation? The entire pole of the planet had flipped. On average, these flips seem to happen every 450,000 years, although the last few have only got 300,000 year gaps between them. Comparatively, it's been 750,000 years since the last reversal. You might think that we're overdue for one, and some have made that claim. However, scientists have found that there's little rhyme or reason to the timing of these flips. One of the longest gaps between flips took place in the Cretaceous period, and it lasted 40 million years. The record holder, the Kierman reverse superchron, was 312 to 262 million years ago, 50 million years with no reversal. Scientists are still trying to understand what causes these flips. However, the current theory is that something, perhaps some interplay between the mantle and the outer core, causes a fluctuation in the core's spinning. This disrupts the spiraling shapes of the core's flow, breaking them down. The magnetic field of the Earth stops being unified and generally becomes a sprawling mess, fighting against itself. Several poles might temporarily arise during this period of shifting magnetic confusion. While in time things settle down and the spirals reassert themselves, it seems random as to which way they will do this, meaning about half the time our magnetic North Pole reappears over the geographical south. This reasserting can take 1,000 to 10,000 years. Alright, but would that really be the end of the world? Why does this matter? Well, during that period before the poles reassert themselves, our Earth's magnetic field drops to as low as 10% of its current strength. In theory, this could leave us much more vulnerable to all the solar radiation space throws at us. We could see auroras reaching much further south during that time. Skin cancer rates would increase. Our satellites would find themselves with not enough shielding. Radiation would fry their circuits, causing them to malfunction, shut down, and potentially even slowly fall from orbit. Our electrical grid would be much more vulnerable to solar storms, which could lead to large segments of the Earth's population without power. With no electricity or satellite communication, It would be a devastating blow to our global civilization. It could be worse than that. A research team from the University of New South Wales in Sydney even linked one of the most recent weakenings of the magnetic field, the Lachamps event, a temporary 800-year wobble rather than a full flip, to megafaunal mass extinctions in Australia, including the deaths of Diprotodon, giant Australian wombats, and Procoptodon goliath, giant kangaroos. Temporary wobbles like this are known as geomagnetic excursions rather than full reversals, and they happen over much shorter time frames. Their transition periods can last as little as 200 years rather than 10,000, which can be much more difficult for species to adapt to. In their 2021 study, they argued that there was a spike in atmospheric radiocarbon levels caused by the collapse of the Earth's magnetic field, indicating climate shifts that could have led to these extinctions. The timing lines up uncomfortably. But how real are these risks? Honestly, it's a mixed bag. A point in our favor is that other than this recent study, there is no indication that magnetic field reversals have ever coincided with mass extinction events. It seems like many reversals have come and gone without affecting animal or plant life at all. And even in this study, such mass extinctions seem to have been limited in scope. There is no claim from the researchers that this was a global phenomenon. Other parts of the world remained unaffected, even during the Lachamps event. It seems that a perfect storm might have been in play, where specific conditions over Australia left it more vulnerable to solar radiation. In terms of our global society, it's worth noting that these magnetic changes would take many lifetimes to complete, even at their fastest. This would be slow enough that we could come to terms with our new reality. If our satellites don't have enough shielding, we would have time to build some that were better protected. If solar radiation becomes a larger risk, we could remain indoors more. Sun cream might become more powerful to mitigate the dangers of cancers, if not remove them entirely. And according to NASA, even if our field were to significantly weaken, it's not like we would be left without protection. Our atmosphere itself can catch radiation, meaning that we would remain safe from solar winds and cosmic radiation, at least to some degree. It would take far longer than 10,000 years for our atmosphere's ozone to be stripped away. But I would be surprised if there wasn't at least some turmoil, at least while we adjusted to living under a reduced magnetic field. Big changes to how a society operates are always painful. And this isn't entirely hypothetical. Did you know the Earth's magnetic field has been steadily weakening for the last 200 years? It would take another 1,300 years for it to vanish completely, so there's plenty of time for it to stop its current downward trend, and there's no reason to think this isn't just a temporary wobble. But on top of that, there is also the South Atlantic anomaly to consider, a section of the Earth's magnetic field that is already showing signs of significant weakening that covers most of the space around South America and the neighboring ocean. This zone might not influence life on the ground, but is dangerous enough that it has fried satellites and threatened astronauts. The Hubble telescope has to turn itself off every time it flies through it. Imagine that, but across the entire globe. That's what we might expect while the poles are reversing. Concerningly, the South Atlantic anomaly has been growing continuously since we started keeping track of it, possibly suggesting the approach of either another geomagnetic wobble like the Lachamps event, or that a full-blown reversal is already upon us. If it happens, it won't likely be something that ends civilization as we know it. But if the study about Australian megafauna is correct, it isn't going to be without impact either. Species could die. Humans will have to accommodate a very different, more hazardous space environment. It's interesting to learn about geomagnetic reversals and their potential impacts on the planet, but while we are not likely to see one happen in our lifetimes, for the generations of humanity after us, this might turn out to be a lot less hypothetical. They might be seeing it firsthand. Well, that was a little ominous, but that's all we have time for today. I hope you weren't too spooked listening to this podcast on magnetic field reversals. If you like what you've heard, please feel free to follow us for more podcasts on other fascinating space topics. But for now, I'm Alex McColgan, and this has been Astrum. All the best, and see you next time.